Hello and welcome to this SeeSAR 10 tutorial. If you're already a user, click on this little icon here and let the program show you what's new in there. I will start as a beginner's guide today and we'll start with a new project. When you fire up SeeSAR, you will be automatically in the proteins mode that's shown here by this protein ribbon on the top in the mode switch button. If you hover over this, you will see that there are many modes in SeeSAR. As you see, all of them are by default empty, nothing in those tables. So we have to fill them with life, and this most of the time happens up here. And we start in the proteins mode and load as a protein. I will use 2ZFF for this example here. It's a thrombin as one pocket. So I click on this and SeeSAR will automatically download this protein from the PDB and extract all the heterogroups. In this case, this is only one. They will be, if it's many, they will be listed here. If you click on them, you will see in the 2D window what's the structure behind this code. In this case, we're looking at the crystallized ligand. And to choose this as the ligand that we want to work with, we select this little radio button here at the front of the row and confirm our selection with this play button here on top. So we are now in the list of the proteins, so there's only one here, and the ligand for this protein is loaded. If I click again on this, I will see it in the 2D and in the 3D. And if I press my space bar, I can zoom in a little bit. And you will see directly that SeeSAR has calculated you the affinity for this ligand, and it's shown in the data window on the left. And you see as well those coronas around each atom. These are the individual contributions of each atom to this affinity score. And a green corona indicates that this is good for your binding affinity, whilst the red corona indicates this is bad for your binding affinity. And the bigger the corona, the stronger is the effect. For those of you who might be red-green blind, I can only suggest to change that settings here in the appearance settings. We can go to the blue-green mode, so everything that's good for affinity or good in general will be depicted by blue symbols then. As most of you are not red-green blind, I will switch it back to the standard setting, but I might set the whole theme to a light mode. So all the tables and all the background will be in a lighter depiction yet. This is really good when you work on a projector. Probably when you work long hours, the dark mode will be better for you. The light mode is just easier to see in different light settings. And equally, you can change the background of the SeeSAR window, the 3D window. So I will set this now on white. I hope this is better for this recording. Okay. So if you want to work, no, maybe I should mention that the buttons here on the top right, where I just set my appearance, are all mode independent. So they will ever be there, whatever mode you're in. Whilst here on the top left, the buttons change according to which mode you're in. So we are now in the proteins mode, so we have only the option to load something. The analyzer mode is really good for understanding the binding mode. I've hit the spacebar again to zoom in. As we have selected the binding site, our score has disappeared, which makes sense. If we had made any changes and removed some amino acids which are crucial, the score would of course change. So whenever we make changes to the binding site, the score disappears. So I'll click on the row menu and say calculate estimated affinity to get our score and our coronas back. So you see them now, and you see not only the coronas, you see as well those green dashed lines, which are our hydrogen bonds. And those are color coded as well. You will see some that are dark green here, and you will see a few that are very light here, like this rather white one. When they are a nice dark green, that means they have a proper shade, proper distance and geometry to form a good H bond. Whilst when they're white, it means that the geometry is a little bit crooked, so they might be a little bit out of the lone pair or in different strange angle. So we'll show you this might not be the best hydrogen bond as well. I think personally the view is a little bit crowded at the moment, so I will clean up a little bit by first clicking on the show binding site only button, which will make everything disappear, which is not part of the binding site. So only the residues which are part of my binding site are left, but I have more options what to toggle off. So I can hide ligands, there are none at the moment. Metals are there, I can hide all the waters, or I can hide the backbone. So I personally want to hide the backbone now. If I click on this, these are all buttons. I can click on this as well. If I have several proteins, I can make them all invisible using this. So now we have a little bit better view of our binding situation here. So SeeSAR is designed to help you really understand what's going on. I drag my table here a bit wider that we see all the values in the table. And I mentioned before, we have an estimated affinity. This is on a logarithmic scale, so we're somewhere here in the high nanomolar, low micromolar area. And this doesn't really help you to understand much so far. So we explain what each atom individually does with those corona. I mentioned before, green is good for binding affinity, red is bad for binding affinity. No corona means this doesn't do anything for your binding. And if we want to find out why those coronas are there, we go up here to label and measure icon and activate as the label function. You see I have a little label tag next to my mouse now. And I will click, for example, here on this carbon with this red corona. This label might be a little bit tricky to read, so I increase my label size briefly here so you can read this better. Okay, so we see that this red corona is there because there is a desolvation problem on the receptor side. So yeah, our scoring function HYDE stands for hydrogen bonding and desolvation. So you see the hydrogen bonding, the interaction line, and the desolvation line. And you see always ligand-wise and receptor-wise why those lines, why those values exist. And you see interaction line is 0. Okay, there is my H bond, that makes sense. Desolvation line for the ligand is minus 1.5 kilojoule per mole. Okay, when I look at the binding situation here, I see that I have a aromatic carbon, which is now inside the binding site, which is good. I've taken it out of the water. The receptor itself seems to be unhappy. So if I want to find out even a bit more why this is like this, I can click on this little eye here and we'll get those pink lines, which highlight me the contact points of this carbon with the binding site. And I see that this sticks right to a carbonyl function, which is of course unhappy there. Same with the disulfide bond. So I'm having this carbon here in a rather polar area, which makes it, of course, unhappy. So you can activate more labels. You can equally activate torsion coloring. So you can look if those angles, torsion angles are helpful, yes or no, right or no. And you can analyze if you believe the binding there, yes or not. So I personally find this very helpful to understand why the score is like this. I personally want to see the surface of the binding site as well, so I activate this here. Okay, so we see how we occupy this little sub-pocket here. Maybe there's room for growing into the back pocket here as well, but it fits in a really nice geometry in there. If we take this little drop down here, we have more options on the surface, so we can color it by element or by hydrophobicity, which I find personally very helpful. So I can see the yellow areas are hydrophobic areas, the blue areas are hydrophilic. So good to see which atoms are buried in what area. And basically this reflects what I said before, or what I guessed before. I have this aromatic carbon here pointing towards the hydrophilic surface. Of course, it's unhappy there. If there are areas that I can't see very well, I can activate this relatively new clipping here. And so I cut off the binding site a little bit, and I can change those settings by moving the clipping planes up and down. So when I activated this button, I have the coordinate system, and I can pull this a little bit up or to the side to clip the binding site according to this coordinate system. Equally, I can rotate the planes a little bit around, so you see what part of the binding site I want to clip exactly. I actually want to see a little bit more of this. Right, perfect. You can flip it around as well or reset it to the center of gravity. And when I deactivate this little clip here, I see a little bit more of my binding site than I did before. Okay, so binding site is the one thing. Unoccupied space is the other thing. So when I activate this setting, I can see where there's room for at least a fluorine between my ligand and the binding site. So I would say, having looked at the binding mode now and seeing where there's room for optimizing my molecule a little bit, I have some ideas how I might edit this molecule and how I could improve its affinity. So to do editing in 3D, we take this molecule by clicking on the row menu again and adding it to the molecule editor. You will see that I'm now in this editor mode, and up here is a full bunch of new icons which allow me to modify the ligand by adding atoms, changing element types, changing charges. You see, whilst I'm hovering over those icons, you always get a tooltip telling you what you can do with those buttons. And equally, you see that now my coronas have disappeared. I see now all the hydrogens to show me where I can add more atoms onto the molecule. If you want to get the coronas back, just to remind you where there were good and bad areas on the binding site, you see I can click on the table again, my coronas will be there, but my editor icons will be locked. So to start the editing, I press the resume button again. And so we had this red corona here, and we've been in a very hydrophilic environment. So what I'm going to do first is shield this carbon by adding an amino function. So now I want to know, of course, if I did a good or a bad change. To find this out, I save this edited molecule to the table, and SeeSAR will calculate the binding affinity for me, and we see I just gained an order of magnitude. And this is, of course, something that surprised me a little bit. I've expected a little improvement, but not that strong. So I click on this and look what happened here, and I actually created a relatively good green corona instead of having this red corona here before. So nice change so far. Let's try to go on a little bit. You see that here's room around my 5-membered ring and the aromatic backbone here. So maybe we just bring this a little bit closer together and add a little carbonyl group here. Let's see what happens when I bring this to the table. And we will see I improved my affinity a little bit more again. So all looks good. This is maybe the first few good edits that I made here. I'll turn this fog off because this is getting a little bit irritating to me, or confusing, better said. And like this, you can go on playing around and editing the molecules, adding atoms, or maybe just closing a little ring here. You see SeeSAR automatically sets bond angles and length when you're editing this, but the molecule is not fully minimized. That only happens when you are bringing it to the table. And you will see that SeeSAR starts moving your molecule around already during the optimization process, because now you have a big red corona here around this carbonyl group. When I go back to my starting point, you could see this was still forming an interaction. So what happened here, if I want to compare how my molecule has moved, I can click on the row menu and set my starting point as a reference. It's now colored in purple, and it's indicated here by this little color palette here in purple. When I click on the second one, the purple area still stays, so I can see how the angle of my carbonyl has moved, so it can't form an H bond with this backbone from the glycine 216 anymore. So you see how this is a little bit of playing backwards and forwards, and I ran now into a situation where the molecule might be of my interest, but I have moved it to a position where it's a little bit unlucky. So let's try to find a position for this molecule which is still able to form an H bond here. And to do so, we have to start a docking, and docking happens in the docking mode. And as I want to dock this particular molecule, I will click on the row menu again and add this molecule to the docking mode. So we are in the docking mode. I have my one molecule here in my input library. And to do a docking, I do have to do nothing else but pressing this particular generate posts button. And the docking has started already. And if you want to apply pharmacophore settings to this, this would be the button here at the very first. Equally, you can change the number of docking solutions that are produced. We have here 10 by default. If you are working with more computational chemists, then you can export the docking definitions that you've set here and can send this docking out to a cluster or a higher power computer and do a bigger throughput. Okay, so here are my solutions. I can click through them, but they're not having my coronas. I want to see my coronas. So I can either click on the row menu, as you notice already, and calculate the estimated affinity. as I, of course, don't want to do this for each of those docking solution individually, I can use those check boxes, or I can use the checkbox on top and say check all for me. Go here to this calculator icon and calculate the estimated affinity. Maybe a generalized word here, all the options that you have for each individual molecule here in this row menu are listed here on top of the table as well. So all the calculation functions are here in this first calculator. The option to add one molecule or several to other modes are here in the second mode button. You can export molecules to a file. For example, here, if I wanted to save those docking solutions, I could bring them now to an SD file. I can launch StarDrop if I want to know more about ADME parameters, and I can send all those molecules to be references. But for now, we want to inspect our docking solutions. So this is the one we're looking at right now. You see it has moved a little bit off, so I'm able to set up this hydrogen bond again. Let's look at the one that's the best. You see here now by the score, this is the best. You can click on the column header as well and see the table would get sorted. So you have the best molecule automatically on top. And you see here, now I make this hydrogen bond, but I lost the other one. So this one here is really favorable, and we could find another 8 bond down here. So you see there's different solutions, and if you want to compare them, you can send all of them to being references. So you have a nice idea of how the binding site was explored. Some of them make more sense than the other, as you can see by the score. Okay, let's remove them all as references again, and let's discover the modes that we haven't discovered yet. We have seen that in the editor, we can make own modifications to the molecule in 3D. But if we might run out of ideas, we would use the Inspirator. So let's take our crystalled, our designed molecule, or let's better take the molecule, which is the one that we have started off, which is stored in our analyzer table, and take this molecule over to the Inspirator. So SeeSAR is telling me that I have to configure my Inspirator settings because I haven't used this mode before. And I go to my system settings here and go to the Inspirator settings. And you see that I haven't selected a recore index yet. If you don't have any recore indices, please press this button. It will automatically prompt you to the Biosolvit website. You can download it and store this on your computer, and then select the recore index that you have chosen, and go to here and select the RSX file. Right, so now we have a valid recore index and a growing file. The growing file was delivered automatically with the executable. If you have your own growing files, then you can select them as well and use them for the growing. Okay, so we apply the settings and go back and close our system settings. And now we can use the functionality here in the Inspirator. So the Inspirator allows you 3 things. It allows you to replace a core that you might not like. It allows you to merge 2 fragments or 2 molecules into one. And it allows you as well to grow out of a bond into a particular subpocket. So one case is pretty clear. We've seen that we have the subpocket here in the back that we haven't properly explored. We could see there was a tunnel earlier. So what I've done is I've clicked on one of the bonds, and you see there are little conical pink shapes, and the way they point, so they will show which part will be replaced. The dark part will be the one that's replaced. And this happened already. You see here in the table are many new solutions. I follow the usual scheme. I check them all and calculate the estimated affinity for all of them, because I want to find molecules that are better binders than the one I've started from. And this will take a moment because we have selected quite a few molecules here. And whilst this is calculating, I can tell you again that we have all the values here in the table, which show us if our molecule is clashing with the binding site, or if it has any intramolecular clashes or strange torsion angles. And the affinities are now all here. you see that a few molecules couldn't be optimized. So they must be clashing really, or have been clashing really badly in the beginning with the binding site and were moved away from it. I click now on the header of the estimated affinity column to sort this by affinity. Here is the molecule I started with. You see this by this little ribbon icon here in the source column. So this was the one we've put in there. And you see that we found quite a bunch of molecules which are better than the one we've started from. So to look at, we click just on them and we see how they have nice coronas, green coronas. The new part is highlighted in pink, in orange, I'm sorry. And you see many, many new solutions. This one here has a red torsion, so I might activate the torsion coloring, which is in the visualizations tab as well. You can see this a little bit bad now here under the orange, but as well we could get the label function bad and see that this is a little bit out of the usually observed torsion angles. And so we can go through the list and look at all those suggestions that SeeSAR made us here. This is actually quite nice. And keep an eye on things like ligand, lipophilicity index, and all the parameters that are important for us. So if we find a few solutions that interest us, for example, this one, I unchecked them now all. Let's say this one and this one and maybe this one are out of interest for us, then we select those molecules and we bring them to the analyzer mode. Oops, wrong. I wanted to transfer those molecules to the analyzer. My mistake. Okay, but this was only one part of the Inspirator functionality. The other part would be the core replacement. So I press resume and I'm back to the same starting point. As I said to you before, those little cut points here are directed. So now you see I can turn this around. So let's say I want to find a new ring here. I don't like the 5-membered one. So I've selected those 2 bonds. You see they point towards each other, those little conical shapes. And there's a grayed out part in the middle. And you see that now here this record button is activated. So I click on this and I will get automatically 10 new solutions, which are in the 3D space in a similar arrangement like the cuts that I made here. So SeeSAR tries to keep the 2 bonds that I've cut here in the same place and goes through a library of 3D cores, which will it put in between. I will sort now back by the input file order because my new molecules will be at the end of the table. And I can see that SeeSAR found a few new cores which fit relatively nicely in here. Again, I'm lacking my scores, so I will select those 10 new molecules and activate the estimated affinity. Calculate it, sorry. And we will see now the affinity values. So we can click through them and see if we like any of our new suggestions. You see that the molecule moved in the second step around a little bit. In the optimization step, SeeSAR tries to optimize the hydrogen bond network and moves the molecules around. Therefore, new red coronas come up. And if you like any of those molecules, feel free to transfer them to the analyzer table again. I don't like all of them, so I press the resume button and click just the report button again. And we will see if we find some molecules that are nicer than the ones I found in the first place. So Recall will always find 10 solutions, and it will always find the ones which have the lowest RMSD to those 2 cut points. You can see this in the, sorry, I need to scroll down in that table a little bit. When you see here in the RMSD deviation column, how close the molecules are to the starting point. So SeeSAR will always try to find fragments which have really low deviation to our scaffold. And the more I click, the more solutions I get, but they might have higher standard deviations to the starting points that we have chosen. So I select the new ones as well and calculate the estimated affinity. And Yeah, we go back to the end of the table and see, oh, now we have actually found a few that make some really nice interactions. This is really close to our starting point. It's just a tire sole. And yeah, you see how you get new ideas. We'll take a few of them with us again. I'm too lazy to uncheck them all manually, so we go on the top box and uncheck them all. And now we select the ones that we liked, namely this one, and this one. And we take those molecules over to the analyzer as well. Good. The analyzer mode is now filled with a few new suggestions, and this is what it's made for. It's good for doing hit triaging and selecting the molecules we like. And this can be done by several things, for example, using those little filters here. If we click on the filter panel opens up, and I can check, for example, and keep only the molecules which have, let's say, more than 3 hydrogen bonds. And we lost already 2 of the molecules. So maybe these were not the best ones to look at. You can filter by ligand efficiency as well, but maybe we should make a few more columns visible for now. So here on the right-hand side, you can change the number of visible columns. And let's say we like our ligand efficiency. We want to show it all of the time. Let's say we're interested in the molecular weight and the log P as well. And maybe some of you know that we collaborate with a British company, which is named Optibrium. They're really good in predicting ADME parameters. So if you're interested in ADME parameters, activate the ones, let's say log D, that are important for you as well, physicochemical parameters rather than ADME in this case. So let's have a look at the table. I dragged it a little bit wider. And we'll see that we have quite a big range of parameters here already in the molecular weight, in the log P, and in the log D. If we want to compare this a little bit better, the molecules and their parameters, I can switch the settings here or the view to the grid setting. So I see all my molecules next to each other as well. And each of those molecules has a little radar plot here. If I hover over them, I will see this a little bit enlarged. Equally, I can click on the settings button here to change how this little radar plot looks like. Not only I can adjust my scales, say our molecular weight scale should be going to 700 grams per mole, but we like only molecules that are up to 550. And log P, I don't like any molecules which go over 4, but I allow the scale to go to 5. TPSA, I leave it at the default setting, and I can equally add more things like, let's say, my Herc IC50. I don't want to good Herc IC50. So I go from, let's say we go to 9 because not allowed. Interesting. So we stay with 5, but only allow up to 3. You can add more parameters. Say we don't want any molecules that don't do any hydrogen bonds at all. So if I apply and close this, you will see that the radar plots are updated now. If you have to go through a large number of molecules, I can recommend you to set a few of those parameters up, and then you can directly see the bigger the green area is, the closer you are to where you want to get. You will see that the area colors red a little bit if you have some molecules going over the value the area that you've selected to like. So here you see the Herc is a red dot, and that means the value of this particular compound is over your scale. Okay, so equally you can make a selection here. You've seen, for example, that this molecule here was rather nice with our parameters, so maybe we add this as a favorite. If you're working in a collaborative environment, you can annotate this molecule as well and can say, I like this, and save this for my colleagues. You can, of course, leave more useful comments like nice hydrogen pattern or whatever you want to tell your colleagues. Okay, so for now, we've done a lot with the molecule, but we can work with the protein as well. For this, I go back to the proteins mode. And let's start with superposing 2 molecules. So I have loaded 2ZFF. I will load 2ZDA as well. it's another thrombine as one pocket, and SeeSAR will download this other protein as well. You see here I have a buffer molecule and I have a ligand similar to the one that I've had all the time. So I select this one to be the ligand again and load this. You see that they're relatively close by default already, but as I have selected a binding site on one, I can align those two binding sites by clicking this button. SeeSAR has moved them now on top of each other as good as possible. You see that those sequences here are aligned as well, and you don't have any gaps. I'll switch off the secondary chain of the second protein as well. And if you have a little bit more dissimilar proteins like now, you might want to get a better overview on how they are similar and unsimilar. So you can use this little eye with a minus here and switch that slider over to similar and dissimilar, and SeeSAR will make disappear all the parts of all the side chains that are more dissimilar. Oh, sorry, how to explain this? So SeeSAR will calculate the RMSD between two side chains at the same position and will make them invisible when their RMSD is below 2.0.2 angstrom, like in this case. Maybe I should change the coloring of the protein a little bit, which I can do by clicking on this little color palette here. Let's make one of those molecules green, one of those proteins green, and the other one we make, I don't know, purple. So we have a better overview, which is where, and we see directly which parts of the molecule are a little bit, which side chains are a little bit apart from each other. Where are the differences? You have the same here in the sequence view, only those are still here where the RMSD is above the threshold that we've chosen here in this settings. I've reset this now to see all of them again. And if I have, let's assume, binding sites where I want to mutate a molecule or a protein side chain, then I can take my protein and add this protein to the protein editor mode. SeeSAR will start a duplication of this protein now. You see this, it's called _1 already. This is like, you know this from the molecule editor. You select something and then you can act on this, and you can do the same as before, add atoms, change element types, change bond types, rotate things around. Especially the rotate function is really helpful for me. Sometimes when you have an arginine that doesn't do the interaction that you are expecting it to do, you might tweak it a little bit towards the binding site. Or you can do mutations. Let's say I have here my tyrosine. I double click on this and now it's in the active state. I can select the hydroxyl function and can just put it into the bin, making a phenylalanine from it, and save my edited protein to the table. I could as well select another amino acid and modify this one. Let's say I want to move this carboxylic acid a little bit towards the inside of the pocket. So I can use this little slider here and turn this around to any other position. And now I save my protein, newly edited protein, to the table. It's here called 2ZFF_1. If I want to work with this, I add this again to the protein mode. And now we see this as well. And maybe we color this in purple. And you see here how the carboxylic acid from the glutamine 217 is now sticking towards the binding site. Equally, here is a phenylalanine. The hydroxyl group is missing now. So you can change amino acid types there as well. So you can do a little alanine scan kind of in the computer briefly by mutating your amino acids around. Okay. I think I've showed you most of the functionality of SeeSAR today now. If you have more questions, please contact us or check the help function in the first place. Help function is case sensitive, so it will give you information according to what you've done last. So I've switched the mode, so the mode switch button is my last thing. If you click on this, you will get a beginner's guide, which shows you a few slides on how to get started. Here are you having access to our tutorial movies or a little bit of online help. And if you have questions, get in contact with us. If you want to store your SeeSAR session for the next thing, for the next run, you can go to the Save project or Save project as, and in the About section again, you find contact information if you need to get in contact with us because you have questions I haven't covered today. Right. I thank you very much for your attention and watching this, and hope to see many active molecules designed by you. Thanks.